In the last lecture of this series on visualization of functions, we will consider the following. H of xy equals x divided by 2 minus 3y divided by 2, comma 3x divided by 2 plus y divided by 2. As you can see, h takes two real numbers xy and returns again two real numbers. It is a function that goes from r squared, so the Cartesian product of r times r, and has as a codomain r squared, the same. This function represents the rotation counterclockwise by 60 degrees. We see on the left the domain of h represented by Euclidean plane and the two coordinate axes, and the codomain is a copy of the domain. It's not the same as the domain, it's just a copy of it, so two-dimensional Euclidean plane with the two coordinate axes. And the map h goes from one to the other. As usual, we fix a point P in the domain. In this case, P will have two coordinates, 2.87, 2.19, and its image as well will have two coordinates, negative 0.46 and 3.58. There are three remarks. So as I said before, I anticipated that h is a counterclockwise rotation by 60 degrees. I of P, again I is the map that goes from the domain to the graph. By definition is the pair P, comma, the image of P. For the map H, both P and H of P are a pair of real numbers, and if we write them in a row, we will get this quadruple of real numbers, 2.87, 2.19, which account for the point P in the domain, and negative 0.46, 3.58, which is its image. Now the graph is going to live in R4, and we cannot draw R4 in any way on a screen. In this case, it is not going to be possible to represent the graph of H. We have to sort out some other way of see the action of H of elements on the domain. As done in the previous videos, we now draw the image of few more points randomly picked from the domain. There are about 10 of them, I guess. Once again, we have points in the domain on the left, their images on the right, and arrows connecting them. From this representation, we cannot really guess that this is indeed counterclockwise rotation about the origin by 60 degrees. It looks like that H is acting quite randomly on these points, and certainly not in a structured way like a rotation. So why is this the case? Let's draw again the image of the same points, but each of them in the domain are connected now to the origin with a segment. The best way to highlight the rotation is to see the effect of it on some segment instead of just a point. If we now concentrate, instead of the arrows connecting the domain and the codomain, we concentrate on the segments connecting the points in the domain to the origin and in the codomain to the origin of the codomain, we can now have a better idea of the action of H and really convince ourselves that it is a rotation, it is a counterclockwise rotation as stated before. Now the image of this map is all r squared. This can be shown by using the theory of linear transformations that we will cover in a future section. There is still open the question of, in this case, when the graph is in a too high dimension, is embedded in a too high dimensional space, so we cannot draw it. How can we display the action of the map on the domain? The representation of the number 2, as I stated in one of the previous lectures, introductory lectures on the visualization of functions, was the representation of the function by means of its image. So we were taking the whole domain, applying the map to every point in the domain, and see what the image of the whole domain looks like. This particular case, one can show that the image is all r squared, so it doesn't give us much information. Therefore, we can apply the same concept to some particular subsets of the domain. For example, if we take some subsets that have some geometrical shape, in this case I have fixed a circular region like a disk, and then a rectangular region. We can concentrate the action of h to these two regions and draw in the codomain their images. This is the only way we can actually to represent in some way the action of h. So what happens if we do that for h as defined before? So these are the images of these two regions. In this case, we clearly see that the map seems to be a rotation about the origin, because both of the figures are rotated by a certain angle around the origin. Now, as I stated before, the angle is 60 degrees, and this is perfectly compatible with this with the image that we are seeing now. Sometimes it is too complicated to keep domain and codomain separated when drawing a function whose graph is not representable. It takes too much room. So what you can often find around in the textbooks is just a unique coordinate system of two axes, in which people represent both the domain and the codomain of the function. So in this case, to reproduce that situation, we are going to translate the green coordinate system onto the red coordinate system. So this is what usually one sees when applying functions whose graph is too high dimensional. You see the domain and the codomain, if they are the same, of course, so if they are the same two copies of the same space, then one can represent them in this form with certain geometrical objects in green. Well, in our case we denote them in green, and their images in the same coordinate system. We can repeat exactly the same procedure for maps starting having domains R3, so the three-dimensional Euclidean space, and having as a codomain R3 again. This finishes this series of lectures on the visualization of functions.